Hey everybody, it's time to get started again. Let me start with something of a buzzkill, all right? Today marks about the midpoint for the first part of the Bio 1120 class, all right? And so remember that the class is essentially divided into three parts, punctuated at the end by an exam. The first exam for this class will be 2 weeks from the next time that we meet. So this is the second week that we've gone through 2 full weeks. We've got this sort of intermediate lecture today, and then we'll have 2 more weeks of lectures, but 2 weeks from Thursday will be the first exam for the class. So again, I know that's something of a buzzkill, but I want to emphasize this. I want you guys to do really well on that first test. I want you to break records for me in terms of the average score on the first exam. And I'm trying to figure out ways to help you all to do that. The single best thing that I can tell you to do is look at some of the old exams that are available to you on the pilot page of the course. If you haven't been doing that already, and I know that many of you have, I can tell, but if you haven't been doing that already, this would be a swell time to get started doing that. Okay, and what that's going to do, when you look at those old tests, there's a bunch of good things that will happen for you. One of them is that you'll realize, if you look at 2 or 3 of them, that I recycle a lot of questions. All right, and you'll get a sense for just how much I recycle those questions. Okay? Embarrassingly, quite a bit. All right, so you'll find that from one exam to the next, that something like a half of the questions are pretty much the same. So that's going to help you right out of the gate get those questions under your belt and comfortable for when you see them a couple weeks from now. But another thing that you'll notice is that when I recycle questions, I'll often tweak them just a little bit. And I'll admit, I have sort of a guilty pleasure here. I love it when students come to me and they say to me, gee, in the 2012 version of this question, the right answer was A. Why is it that on today's test, the answer is B? And I love thinking to myself, it's because I changed the question just a little bit. All right? And so look for that too. Look for how it is that I'll change the question so that you don't get tricked and give me that little bit of a guilty rush when you come and tell me that the answer key was wrong because the previous test, a different answer was right. And then, look at the other questions and start to wrap your head around how could those questions be changed so that some other answer would have been correct. That's when you're really starting to get into some learning. The first 2 things are just things that are going to help you get a good score. That third thing, figuring out how to tweak the question yourself to cause another answer among the choices to be correct. If you can do that, you know this stuff. You're learning this stuff. You're getting a good grip on the concepts that I'm hoping you'll take away. And that is cool. Everybody should be excited if that sort of thing is happening. All right? And then fourth, last but not least, when you look at those questions on the old tests, I think it's going to give you some insights into the sorts of things that I think are important and the way that I like to ask questions about those things that I think are important. You don't want to be surprised by either of those 2 things on the day you're sitting here taking an exam, right? You want to come in as if it's your second, third time through the mill with me so that you're in good shape, you're relaxed, you're comfortable, you're ready to go. All right, so take a look at those old tests. I looked at them last night. My recollection, excuse me, my recollection is there were 7 or 8 old exams that you could look at and a similar number of answer keys that you could look at. If you really want more, I can probably dredge up a few more for you, but I think that should be plenty. Bottom line again, gee, I've talked now for 4 minutes. And all I'm really trying to do is encourage you, please take a look at some of those old tests that are available on Pilot. It's going to help you guys do much better on that first test. And this is a great time to do it. Half of the questions that you see on the tests, those old tests are going to be like, gee, what's that all about? I don't know anything about that. That's not been talked about. But half of them are things that you will recognize that I've been talking about during the course of the lectures. Okay? About the tests, it's bound to be crossing some of your minds. What else do I need to know for the tests? Do I need to know what's on page 62 of the textbook in the upper left-hand corner? Unequivocally, absolutely no. Right? If I haven't talked about something during the course of a lecture, I don't think that's fair for me to ask you about on an exam. Okay, so you don't need to worry about memorizing things out of the book. Use the book as a way to sort of verify what it is that you thought you heard me say. Check out the cool pictures, that sort of thing. But if I haven't talked about it in a lecture, I'm not going to ask you about it on the exam. And by the same token, things that come up in the laboratory part of the class do not necessarily mean that they're going to come up on the exams for the lecture part of the class. Now, of course, in lab last week you worked on pH, and I've talked with you a lot about pH, so there should be some overlap. But if it only got talked about in lab or dealt with in lab, I'm not going to ask you about it for the lecture part of the course. They'll be separate in that way. Okay? So, if you haven't done it already, take a look at those old exams on Pilot. Okay? I think I'm getting feedback that the sound stuff is working with these recordings. Just in case you were burned by the first one or two where they hadn't been getting the sound to work on the integrity recordings of these lectures, that doesn't seem to be a problem anymore. So just so you know, from here on out, pretty much every lecture should work pretty smoothly. They'll all be available typically in an hour or two after we're done with the lecture. You can watch them also on the Pilot page for the course. Okay. Any questions for me now that I talked about that unhappy day, October 1st, the first exam for a class? Good. Okay. So here's where we're at. I've been talking with you about esoteric things like what it means to be alive. I've been talking with you about subatomic particles. I've been talking with you about how you put those subatomic particles together to make atoms, and the atoms in turn can get strung together to make compounds. And I think you guys now are in a place where you can look at a compound and you probably have some dreams, nightmares perhaps, about looking at a molecule and knowing everything there is to know about it. It's sort of like pigeonholing or stereotyping. I can look at you and I can tell you all about it. You should be able to get the essence of the chemical behavior of any compound now just at a glance by applying these relatively few rules, two really, that we've been talking about. And today, for the first time, we're going to start talking about biologically, I was going to say biologically important molecules. All of these molecules are biologically important. Water certainly is biologically important. But now I want to talk with you about things that living things are really orchestrating and pulling together and making molecules, making some really big, important molecules. So in today's lecture and on Thursday's lecture, I'm going to talk with you about the four classes of biopolymers that all living things rely upon. And I'll steal all my thunder. In a nutshell, here are the four major categories of biopolymers that we'll be talking about. I'll be talking with you about carbohydrates, I'll be talking with you about lipids, we'll talk about nucleic acids, and we'll talk about proteins. Okay, so those are the four biggies. Today, my plan is to touch really just on the first two, frankly the most boring of those two, so that I can have a lot of fun and I can get excited and bounce around on Thursday when I talk with you about proteins, and then my personal favorite, the nucleic acids. So that's something to look forward to on Thursday. Today, though, the primary focus will be on carbohydrates and on lipids. Okay? Before I get to that, though, let me just rewind a little bit. At the end of lecture on Thursday of last week, I talked with you about these seven functional groups that show up time and again in biomolecules. And they're going to show up a fair bit again today, even when I'm talking with you about carbohydrates and lipids. Here's that list of 7, as we went through them at the end of class on Thursday. And let's just talk about them again. I'll flash them up. Less than 2 minutes for each of these 7, maybe less than a minute for each of the 7, just to warm us up, warm me up, and get us thinking about what you can infer from the structure of a molecule like the ones you see here. And in keeping with this talk about an exam coming up, let me also remind you of a couple of things that you just kind of have to buckle down and memorize. The names of these things. Unfortunately, there's no trick to it that I'm aware of. You just kind of have to learn the vocabulary, and that means memorization. When you see a molecule has one of these functional groups attached to it, an OH, OH groups are called hydroxyl groups. And when you attach a hydroxyl group onto a carbon molecule, you've made that carbon molecule into something that we call an alcohol. All right? There's a picture up there for you of a specific alcohol. It's one where the carbon chain is only 2 carbons long, and we call that ethanol. You don't have to memorize ethanol. You may as well. It's an easy one. It comes up a lot, but I'm not going to quiz you on the test saying what's the chemical structure of ethanol. I may quiz you on the test and say what kind of compound is this? And the choices would be something like an alcohol, an amine, an aldehyde, a ketone, right? I'll give you those sorts of things. One of the 7, is it a phosphate? I'll give you those sorts of things. This, because it has a hydroxyl group, you would say is an alcohol. Okay? That's sort of the memorization aspect of what's on this screen. A hydroxyl group is an OH. When you put an OH on, it's called an alcohol. But here's the practical insight, sort of the concept that's important about alcohols, about hydroxyl groups, is when you put a hydroxyl group on a carbon chain, you put onto that carbon chain a little patch of hydrophilicity, water friendliness. Okay, so if that OH that's shown in blue there was an H, that's ethane. That's a gas that's very inert. It wants to have very little to do with water. It's not very water soluble. You put that hydroxyl group on there and you make it into an alcohol. Now you've converted, it's a complete transformation of the chemical behavior of this compound. Instead of being a relatively inert gas that's relatively not, or that can't be well dissolved in water, putting that one little change on there causes it to be an exceptionally water-soluble molecule that has a little bit of chemical activity because it has, with that OH, with that hydroxyl, a little bit of partial separation of charge. Okay? The H will have a whiff of positive, the O will have a whiff of negative, and that makes all the difference in terms of the chemical behavior of this molecule. Okay? So those are ethanols. Those are alcohols. That's ethanol. Let's talk about another one. 7 of these groups. Number 2 on the list were the carbonyl groups. A carbonyl group is when you've got a carbon that instead of having a hydrogen dangling off of it, you get rid of 2 of its hydrogens and you lock on an oxygen with a double bond. Okay, that's the functional group. On this particular slide, those are called carbonyl groups. If you have a carbonyl group in the middle of a carbon chain, you call that an acetone. If you have it at the end of a carbon chain, you call it a ketone. Okay, so acetones and ketones are what the molecules get called when there's a carbonyl group involved. Those are the things to memorize. Practically speaking, sort of conceptually, what does this structure say to you? Well, once again, if you didn't have that oxygen here, you would instead expect to find a pair of hydrogens. That would have been a 3-carbon long molecule. no partial separation of charge, lots of covalent nonpolar bonds. Those guys are going to be, that's probably going to be a gas. It's going to be chemically relatively inert. You certainly would have a hard time dissolving that in water. But you put a carbonyl group on there, and what's going to happen is this oxygen is going to be pulling electrons toward it, away from the carbon. The carbon, in turn, will start pulling some electrons away from the other carbons that it's associated with. You'll get a diffuse positive charge running along the carbon chain. You'll get a little bit of negativity there by the oxygen. That's going to make this a relatively soluble molecule in water. It's going to be hydrophilic, friendly toward water. Okay? So, that's the sort of thing I hope just sort of springs to mind when you look at a structure like this. I haven't committed that sort of thing to memory. I'm kind of doing it on the fly as I look at these structures. And how's this going to play out? Oh, the oxygen's going to pull electrons toward it, and then the rest sort of follows from there. So here's a third one. Here are carboxyl groups. A carboxyl group is a carbon atom that has a double bonded oxygen and a hydroxyl group. So in a sense, it's like a double whammy. We've got both the hydroxyl group and the carbonyl in play at the same spot now, right? And so if a hydroxyl group makes a molecule water soluble, and if a carbonyl group makes a molecule water soluble, what do you suppose happens when you have both of them on the same spot? Now this is going to be, even more so. It's going to be at least additive and maybe even multiplicative in terms of the effect that it has on the chemical behavior of these molecules. So if you put a carboxyl group on something, you end up making things that are going to be called an organic acid or a carboxylic acid. And you're also going to end up with a patch on the surface of this molecule that is pretty chemically reactive, because what's happening here sort of conceptually is this. This oxygen is going to be pulling electrons away from that carbon. This carbon, in turn, is going to not have as much of an inclination to give electrons to this oxygen when it comes knocking on its door. And with this oxygen still going to be hungry for electrons, so it's going to beat up on that hydrogen. And that, in turn, will often result in a dissociation where the carboxyl group gets ionized, meaning that the hydrogen, that one little lonely proton, goes floating off by itself, and its electron stays permanently associated with that oxygen. So whereas with a carbonyl group or a hydroxyl group, we're talking about partial separations of charge, delta plus, delta minus. We're talking about polar covalent bonds. Here, we're talking about an ionization where you've just lost. You've got a full positive charge and a full negative charge that have become physically separate from each other. That positive charge is going to change the flavor of the solution that you're in. It's going to lower the pH, but practically speaking, more importantly, we'll probably be focusing most of the time on the effect of the negative charge on the carbon compound. That's going to make a very reactive center on the surface of this carbon molecule that's going to be very interested in rubbing up against things that have a positive charge, or at the very least a slight positive charge. It's going to make for an affinity, a basis of interaction between this molecule and another molecule that's going to be really very intense. There's a lot of interest to balance out that negative charge with something that has some positive charge. So there will be a strong attractive force between things that have a carboxyl group on them and things that have a little bit of positive charge. Practically speaking, how does this play out? What if you have a long molecule, like a polymer, like what we'll be talking about later? If you wanted to have two parts of the polymer bend back and interact with each other, this is a sweet way to pull it off. Put a carboxyl group on one and an amine group, something that has a positive charge, on another part of the molecule, and that will naturally pull them together. Even better, even more fun. Let's say you've got an enzyme, a protein that you want to have catalyze a particular chemical reaction. Why not have on the surface of the enzyme an arrangement of charged things that fit really comfortably with a substrate, with something that that enzyme is likely to interact with or needs to interact with, right? A glove in hand kind of thing. That sort of game happens all the time in biological systems, and we'll get into that more and more, particularly on Thursday this week. Bottom line, if you got a structure like this, a carbon with both a carbonyl group and a hydroxyl group, we call that our carboxylic acid. We say that this structure is a carboxyl group, and we expect it to have a negative charge, okay? Or at least to be inclined to having a negative charge, depending on what the pH of the solution is. All right, now I already mentioned amino groups and what I was saying about carboxyl groups. Carboxyl groups are something that impart a negative charge to carbon molecules. Amino groups impart a positive charge, or tend to impart a positive charge to carbon molecules. When you have this nitrogen with its two hydrogens dangling off of a carbon chain, we call those kinds of molecules amines. And you can see that just like with the carboxyl groups, there's a tendency to surrender that hydrogen for a carboxyl group. The amine groups have a tendency to pick up free hydrogens and in turn get a positive charge that tends to be localized on that nitrogen. And so it's a yin-yang kind of thing, right? These are opposite charges. A carboxyl group and an amino group will have a good basis for interaction. Those two charges offset each other and make the molecules comfortable.
So the way it's up to is if there's a nitrogen with two hydrogen bonds?
By definition, a nitrogen with those two hydrogens is an amino group. And again, there's no trick to it. It's just that's how these things are described. That's the vocabulary. Yeah.
I noticed that the example on the other side actually has a carboxyl group. Is that where we get, and I think that is an amino acid.
It is.
Is that where we get amino acids?
We'll be talking about amino acids at some length on Thursday. This is an amino acid. All right? Okay. So, amino groups. We're in the home stretch. We're past halfway, right? Just this one and two more to go. Here's a sulfhydryl group. If you dangle a sulfur with a hydrogen off of a carbon chain, now we're talking about putting a sulfhydryl group onto that carbon chain. Those compounds that have sulfhydryl groups on them are called thiols. Okay? So that's, we have alcohols, we have ketones, we have aldehydes, we have carboxylic acids, we have aminos or amines. You also have thiols. Just as a word to the wise, if somebody offers you something that's got the word thiol in it, hey, you want some, dihydrothiol or something, just go away. You don't want anything to do with it. Thiols stink. Okay, they just reek. They smell like rotten eggs. Okay, rotten eggs have a lot of thiols associated with them. It turns out the compounds in rotten eggs have a lot of thiols associated with them. I'm tempted to tell you guys a story right now. This is a kind of a dull, boring sort of part of the lecture, so let me liven it up a little bit, give you a little insight in terms of the kind of people that I hang with. I was a postdoc for a couple of years, or for a year or so, at Harvard, just before I came to Wright State. And my roommate, interesting character, he's 24th in line to the Spanish throne. At least he was at the time. He's probably gone down a few notches since then. Neat guy. I'm inclined to mention his name, Francisco Jose Ayala. All right, neat guy. Had a great relationship with Jose, or Zay, as we called him. Well, after I left to take a faculty position here at Wright State, he still stayed behind in our apartment. Okay, we were roommates. He stayed behind. He had something like 6 months left on the lease, and Harvard didn't treat him well, at least in his mind, because he was going to be there for the following year as well, but there was a gap of something like 3 weeks between when it is that he was going to leave our apartment and when it is he could move into his new apartment. Right? And he thought this was extremely unfair. So what he did to sort of stick it to the man at Harvard is that the day that he moved out, he brought with him about a 1 liter bottle of dithiothriotol, a thiol, and he just literally sprinkled it all over that apartment. And he thought it was hilarious because they couldn't. How are you going to pin him with that? Right? Nobody's going to. They walk in, it reeks. They can't tell why it smells. There's no physical damage, and so there's a trick you can play on your roommates. Grumpy old men, they put dead fish in people's cars. A more sophisticated way to do that same trick is just sprinkle a little bit of something that has a thiol. It stinks, and it's virtually impossible to get rid of. It's worse. It's harder to get rid of that smell, I think, than a skunk's spray, which incidentally has a lot of thiols in it. All right. So I think now, with that little digression, you probably have come away thinking that, okay, this guy has weird friends, but also thiols have a tendency to smell. And that's just a small thing about thiols that you should know. I think more important about thiols, what you should know, is we're talking here about dangling an SH off of the carbon chain. So very much like an alcohol or a hydroxyl group, you're just dangling, instead of an OH here, an SH. It has many of the same influences to a molecule that a hydroxyl group would have. So a hydroxyl group puts a little patch of polar covalent bonds that causes it to be soluble in water and reactive with some other things that like to have a partial separation of charge. A thiol in a hydroxyl group, a sulfhydryl group and a hydroxyl group behave very much the same way in terms of the flavor that they impart to the chemistry of the molecule, its behavior. But unlike hydroxyl groups, thiol groups typically are used by living things to make bridges between molecules, covalent bonds that anchor together two different parts of a molecule or two different molecules through what are called disulfide bonds. So you butt one sulfhydryl group up against another sulfhydryl group, the hydrogen leaves, and the two sulfurs end up sticking together with a nonpolar covalent bond. And so literally, living things use them to staple together with covalent bonds different parts of molecules or two different molecules. When we talk about proteins on Thursday, I'll bring this up again. I'll talk with you about disulfide bonds. That's a way to form a permanent association between two parts of a single protein molecule. Okay? So that's the trick that happens with sulfhydryl groups. That's how it is that nature really seems to get a lot of mileage out of them. A secondary use is they can use them to make molecules that are pretty stinky. Skunks have taken advantage of that, right? But their practical application, for the most part, is making these disulfide bonds to cross-link different parts of proteins together. Boring, memorizing stuff, SH, we call that a sulfhydryl group. A molecule that has a sulfhydryl group, we call a thiol. It's in that class of compounds that are called thiols. All right, we're really cruising in to home at this point. Here's a big one, a phosphate group. Phosphate groups have that structure, a phosphorus with those 4 oxygens associated with it. If you want to impart a negative charge to a carbon compound, a really intense local negative charge, there is simply no better way to pull that off than by plopping a phosphate group onto that carbon chain. That's what phosphate groups are all about. Local, intense, negative charge. If you have that phosphate group attached to a molecule, clever name, we call those things organic phosphates. Organic because it's a carbon compound, phosphate because, well, you put a phosphate group on it. All right, and so hence we call those things organic phosphates. And a little bit later today, I'll say a few more words to you about one particular phosphate called glycerol phosphate. You don't have to necessarily memorize that structure, but this white part of the molecule is called glycerol, and if you tack on a phosphate group, we now have glycerol phosphate. If you hadn't had that phosphate group there, pretty chemically inert, not much of a basis for interaction with water or any other molecule for that matter, you put that there and it becomes hugely water soluble in a very reactive compound because you have that intense negative charge. And then lastly, this one's kind of a snoozer, but for good measure, to round out the 7, there are the methyl groups. Methyl groups are a carbon with 3 hydrogens that you tack on to something else, here a carbon compound. So whereas several of the other functional groups that we've talked about improve a molecule's solubility in water, putting methyl groups on does pretty much the opposite. Okay? This is pretty chemically inert, doesn't want to have anything to do with other molecules that much. And if you tack on one of these methyl groups, you end up talking about having methylated the molecule that you put the methyl group onto. Okay, so again, just some vocabulary, some jargon. A little bit of trivia for you. It often surprises people to hear that in an introductory biology course, both this semester and next semester, in each of those 2 courses, this course and the next one by themselves, you learn more new vocabulary words than you do in an entire year of taking a foreign language class. Isn't that something? Right? So for better or worse, I think it's only worse, there's a lot of jargon associated with the sorts of things that we do in biology and in chemistry, and unfortunately there's not much method to the nomenclature for the most part, and you just kind of have to tighten your belts and get to work on memorizing some of these words, because I'm just going to be dropping them like we all know what we're talking about from here on out. So when I say something's been methylated, I hope that conjures up in your mind, oh, he means that somebody attached a methyl group to this compound. It's much more efficient to say this thing got methylated than to say a methyl group has been attached to this compound, right? So again, just a lot of jargon and some vocabulary. There's not much you can do aside from roll around in it and read the textbook and listen to the lectures and roll with those punches. Okay, so there we go. We've got the 7 functional groups of carbon. One more time, nice and relaxed discussion about them. 3 things for each of them. If you wanted to make flashcards or quiz yourself, you need a 3-sided flashcard, right? You need to have maybe a 4-sided flashcard, maybe 2-sided flashcards. So here's what you need. You need to be able to associate the structure of the functional group with the name of that functional group. You need to be able to associate that structure with the name of the compound, which is often related to the name of the structure. And I think most importantly, I hope you don't even need this on the flashcard. I hope you can apply some fairly basic concepts to figure out how that compound or how that functional group will change the behavior of a carbon molecule that you attach it to. Okay? So those are the things I hope you'll take away for all 7 of these functional groups. And it's finally time for me to talk with you about how living things start to work with these compounds. In a word, living things, very much unlike non-living things, rely heavily upon this idea of polymers. Polymers, the concept in chemistry of a polymer is a very simple idea. The essence of it is this. A polymer is when you take a simple molecule, a building block, if you will, and you link one of those to another one of those simple molecules to make something that is twice as big as the original building block was. And then even better, you can take another one of those simple molecules and tack it on to make a chain that's 3 long, instead of just 1 long or 2 long. And then you can take another one and tack it on. That's what's going on with polymerization. So as you make these long chains of molecules, you're making polymers in living things. Here's some more jargon for you. I was stumbling over what I was saying because I just wanted to lapse into the jargon. It's so much easier for me to talk about, instead of the simple individual building block thingy, right? Not a very scientific way to describe it. I wanted to use the word monomer. Polymers are long strings of monomers. Monomers are just the simple, smaller structures that you can string together to make a polymer. So a monomer, mono, one, mer, I don't know, you come up with whatever you want mer to be. It'll be as good as whatever I come up with it to be. But you take these single mono units and you string them together to make polymers. So if you have a monomer and you link it to another monomer to make a polymer, we have a fancy name for that new polymer that's 2 monomers long, right? That's a dimer, di, 2. If you add another one on, that's a trimer. And people usually stop talking about things that are 4 or 5 or 6 long because now the counting system is pretty much mono, di, tri, many, right? So the counting is pretty primitive, but that's generally the way that people will talk about these types of polymers. But again, living things really have gone nuts with this idea of polymerization. You don't find polymers in such abundance in nature outside of living things. Living things, though, are chock full of polymers, and the things that seem to be most important, that living things are most dependent upon, almost always turn out to be polymers, or at the very least monomers that are associated with polymers. So there are non-biological polymers. Nylon, for instance, is a chemist's polymer. You can synthesize nylon by linking together small subunits in a test tube. Chemists have been doing that for a long time. So there are non-biological polymers, but boy, the things that occur in nature and the things that we're going to be talking about for the rest of this lecture and all day on Thursday are polymers, and there are 4 specific kinds of polymers. You can see the names of 2 of them here, carbohydrates and lipids. Again, on Thursday, I'll talk with you about 2 others, the proteins and the nucleic acids. So let's take a look at what's going on with this polymerization process. Again, the essence of what's going to happen here is you're going to take monomers and you're going to link them on to existing either monomers or short polymers to make longer polymers or dimers, depending on where you're at in the process. Let me draw your attention to the 2 action things that are happening in this particular image. There's stuff that's going on here at the top, and there's stuff that's going on here at the bottom. Let's start with A, the stuff that's going on the top. A little bit more jargon for you. When you link together one monomer onto an existing chain of monomers to make a longer polymer, there's a fancy word that we use for those chemical reactions. They are all called dehydration reactions. Okay, so extending a polymer by adding on more monomers, each monomer that gets added on in what we call a dehydration reaction. It's called a dehydration. It's a good name. It's, somebody was clever when they came up with this name. Break it down, right? D means on or removing. Hyd or hydrae here is water, and shun, I don't know, again, you guys come up with whatever you want shun to mean, but we're taking a water out. And if you look at what's going on the top part of this image, you'll see that you've got a short polymer, a trimer, because there's just 3 of those monomers linked together. You have an unlinked monomer, a free-floating guy that's just bopping around. When you link the trimer to the monomer to make, as they call here, a longer polymer, if you want to be fancy, you could call it a tetramer, right? When you add that monomer on, you kick out a water molecule, a hydroxyl group from the incoming monomer and a hydrogen from the existing polymer chain. Always. This is true. These dehydration reactions are true for carbohydrate polymers, they're true for lipids, they're true for proteins that are strings of amino acids, they're true for nucleic acids, for chromosomes. Whenever you bring in a monomer and add it onto a chain to make a longer polymer, that always occurs as a dehydration reaction. For every monomer you put on, you take out one water molecule, or you could say you create a new water molecule. Okay? So dehydration reactions are involved with this synthesis of polymers. And then the flip side, the bottom half of this slide, shows you what happens when you break these polymers down. If you want to take a tetramer and convert it into a trimer and a monomer, you can do that. You can run this polymerization both ways. You can polymerize and you can depolymerize. The way that you take monomers off is essentially the opposite of the way that you add them on. So instead of a dehydration reaction, these are now called hydrolysis reactions. Hydro, water, lysis, break, right? So water is going to be used to break down that polymer into here a trimer and a monomer. Yeah.
Is that where you get, like, when you're reading ingredient labels for stuff like hydrolyzed protein?
This would be hydrolyzed protein if you're looking at a list of ingredients. It's been broken down to some extent. So, note that the new monomers that are getting added on get added on to the end, right? We're not slipping them in the middle. The new monomer doesn't come in between 2 and 3. It gets tacked on to the end. And also note this. The new monomers get added on to one end. That picture isn't by accident, right? It gets added on to the end of the polymer, where a monomer is presenting a free hydrogen. And the incoming monomer has that hydroxyl group that's going to be interacting with that free hydrogen. Polymerization, certainly in living systems, and the way that we use it for lipids and carbohydrates and proteins and nucleic acids, polymerization is a unidirectional addition. Right? You start with a monomer, and you add another one on, and you add another one on, and you add another one on. You never mess with what was happening at the beginning. You just tack things on to that one end. So dehydration reactions are how you're tacking these new monomers on. Again, always at one end of the molecule, never in the middle, never at the other end. And hydrolysis reactions also tend to work in that same way. You take the monomers off one at a time just from one end of the molecule. That's the general rule. Now, there are exceptions to that rule, more so than there are to the polymerization rule. All right, so let's just leave it at that, and notice that we have these two new vocabulary words. You add monomers on through dehydration, and you take monomers off through hydrolysis. Let me talk to you just some nuts and bolts here, give you a sense of the scale of what's going on. So here we've got a really simple polymer. At the end of the process, at the top there, you've got a tetramer, 4 of them long, right? Whoopee, right? Not that big a deal. I'll give you a very specific practical example. This is what's going on when you string together nucleotides to make a chromosome. Nucleotides between friends have a molecular weight of about 500. 500 Daltons is the molecular weight of a sort of a generic nucleotide. If you wanted to make a 1 molar solution of a nucleotide, you would need about 500 grams of that nucleotide to dissolve in a liter of water. All right? We've talked a couple of times about concentration now in this class. And incidentally, that's pretty much all that this week's lab is about. Right? So now I'm making a bridge, a tie into the lab. This week's lab's pretty much focused on concentration of solutions. So if you wanted to make a 1 molar solution of a particular nucleotide, you'd take about 1/4 pound of that nucleotide and you'd dissolve it in a liter of water. Turns out not that hard to do. Those nucleotides are monomers. And the way that living things tend to use those nucleotides the most is not as monomers, but rather as a long polymer. A typical chromosome can be on the order of our chromosomes. The smallest of our chromosomes are over 1 million nucleotides long. So, you know, when we're talking here about what's the word, you know, like monomer, dimer, trimer, tetramer, pentamer, right? What's the word for the 999,362 nucleotide? That's why we tend to go 1, 2, 3, many, right? Because these polymers get crazy long real fast. A 1 molar solution of a nucleotide, about 1/4 of a pound dissolved in a liter. A 1 molar solution of your biggest chromosome, chromosome 1, with something like 200 million nucleotides strung together, would require you to get about a ton, literally a ton of human chromosome 1 and try to dissolve that in a liter of water. The point here is ultimately this. These polymers can become, and here's the fancy technical term, ginormous, right? They can be really big molecules simply as a result of these polymerizations that are going to be taking place. So polymers can be really big, but they start off as these individual monomers that get tacked on one at a time through these dehydration reactions. So here's a zoomed in version of what we've just been talking about. Here's a zoomed in version of what I've just been talking about. And I've said to you now what I want to say about polymers. And it's time for me now to start talking a little bit about one of these particular kinds of polymers, the carbohydrates. Okay? So let's see what some carbohydrates look like, and we'll talk about them. Here are 2 different 3-carbon carbohydrates right out of the gate. Let me toss this out while I've still got your attention, because you guys are going to glaze over before I start talking about carbohydrates. Lipids are the real snoozer of the group, right? That's something to look forward to. Get ready for a little bit of a nap. But before I've lost you, let me tell you, carbohydrates, the word, that name says it all, right? Let's break it down. Carbo is supposed to conjure up in your mind this idea that carbon is involved. Hydrate, hydra, right? Water. So carbohydrates always adhere to this very basic chemical formula. There's a carbon, carbo, and a hydrate, H2O. All sugars, all carbohydrates can be reduced down to this very simple structural formula of CH2O. Put the whole thing in brackets and drop a little lowercase or subscript N after it. For a 3-carbon sugar, like glyceraldehyde, 3-carbon, here N is 3. I'm telling you, it should reduce to this formula. If that's really, I'm hoping I don't get egg on my face for this. I'm pretty confident. You got a 3-carbon sugar there called glyceraldehyde. I'm telling you that molecule can be reduced down to this CH2O N kind of thing. Here N is 3, so that means it should reduce down to this. C3H6O3. How'd I do? Let's count them up. I'm getting a little bit of an adrenaline surge right now, but I'm pretty sure I'm going to win. All right? C3, I said, there's 1, 2, 3. That was easy. It's a 3-carbon sugar. H6, this, if I'm going to have a problem, I think this is where it's going to be. 1, 2, 3, 4, 5, 6. Yes. Right? And O3, 1, 2, 3. How about that? That carbohydrate reduces down, that sugar reduces down to the chemical formula CH2O N, where here N is 3 for this 3-carbon sugar. All carbohydrates will follow that rule. Now, you guys, I'm sure, have jumped way ahead of me here, and you recognize that glyceraldehyde is an aldehyde, meaning that the carbonyl group is dangling off the end of the molecule. as opposed to dihydroxyacetone, which is an acetone, as opposed to an aldehyde, because here the carboxyl group, or I'm sorry, the carbonyl group is associated with the middle of the molecule. All right? Both of these, though, are carbohydrates. Oh man, see, look at that. You guys could have saved me a lot of anxiety and just pointed, I didn't have to count these things. It was already up there. The answer's there. How well do I know these slides? Not well enough, it would seem. But so we have two different 3-carbon sugars that are being shown to you here. One's an aldehyde, one's a ketone, but they're both carbohydrates. They're both sugars. They both adhere to this basic sort of structural formula of CH2O here 3, because this is a 3-carbon compound. All right? Now, well, I got this up here. I want to just give you a whiff of an idea that's going to become more important in another week. In time, I'm going to want to have you guys look at these molecules and think about one other thing when you see them. Right? So right now I'm hoping that you're thinking, gee, is this going to be water soluble or not? Right? So at a first glance, what do you think? Water soluble or not? There's lots of stuff going on here that should make water pretty interested in interacting with that. Right? So I think you guys are all pretty good with that. And in fact, does it surprise you to hear that it's pretty easy to dissolve sugar in water? It's awfully easy to dissolve sugar in water. Now you guys know why. Here are some sugars, that's what's going on. It's easy to dissolve them in water. But again, in about a week, I'm going to start asking you to look for one other thing when I throw a structure like this at you. What I'm going to ask you to do is tell me if you think there's a lot of energy stored in the covalent bonds in these molecules. I don't know that I want to go into it in much depth right now, but I just want you to start to think. And let me tell you what's going on with that. You guys know that electrons in the lowest orbital of an atom have the least energy. To get them to a higher orbital or a further removed orbital from the nucleus, you got to jack them up with some energy. That in turn translates to this. When you've got a covalent bond between two atoms, particularly for a nonpolar covalent bond between two atoms, the electrons are spending a fair bit of time far away from both of those atomic nuclei. They're in between. Remember, the space between atomic nuclei tends to be really great. And that electron will be spending a fair bit of time far away from both. Those are high energy electrons. Electrons involved in nonpolar covalent bonds have a lot of energy associated with them. And if you broke that nonpolar covalent bond, if you let those two atoms go their separate ways, that usually results in the release of a lot of energy. To make the bond, you have to invest a lot of energy. To break the bond, you have to release a lot of energy. When you're looking at this sugar, I'll tell you something that I see. I see a lot of nonpolar covalent bonds, right? Let's count 1, 2, 3, 4, 5, 6. Those are 6 high energy bonds. If you were to break those, you would release a lot of energy. There's a bunch of bonds that aren't such high energy, right? A lot of, the electrons here, this is a very polar covalent bond, or polar covalent bonds. The electrons are closer to the oxygen's nucleus than the carbon, but they're not necessarily equally divided between them, so that's a relatively low energy pair of electrons. Here again, we've got oxygen sucking the electrons toward it, so those tend to be low energy. But nonetheless, that molecule, that sugar, has a bunch of high energy bonds, nonpolar covalent bonds. What do you suppose sugars are good for? Right? The primary role for a sugar in a living system is this is a place where we store energy. Okay? You guys didn't need me to tell you that. That's why those of you who are running in the Air Force Marathon this upcoming weekend, that's why you're going to carbo load. You're going to eat a lot of pasta, right, to get lots of sugary molecules into you so that you have fuel for the race. That's why you put sugar in drinks, is to get a little, that's why soft drinks tend to be sugary. That's why energy drinks tend to be sugary. They're giving you, literally, they're giving you chemical energy to help you drive chemical reactions inside of your body. So for each of these 4 different polymers, I'm going to want to pigeonhole them in terms of what it is that they're good for. All right, what it is that living things are bothering to make these biopolymers for. What you make sugars for, but more importantly, what you make carbohydrates, these links of sugars and then ultimately these long polymers of sugars, what you're doing is you're making things that are there to store energy. Okay? Individual monomers, the sugars, are pretty easily dissolved and transferred from one cell or one part of a body to another. The longer chains, the polymers that we'll be talking about, are better suited for long-term energy storage than they are for transport, right? But pretty much everything about carbohydrates ultimately boils down to this idea of they've got something to do with energy. All right? So let's get to talking about making some polymers, and let's actually talk about some other sugars. So those that I showed you just before were 3-carbon sugars. There's really no practical limit to how long you can make the carbon chain that makes a sugar. There tend to be 3 or so that you find time and again in living systems. Sugars that have 3 carbon chains, 5 carbon chains, and 6 carbon chains. There's no rule against 7, there's no rule against 4, there's no rule against 12. It's just living things seem to have gravitated to a reliance. We see time and again 3 carbon sugars, 5 carbon sugars, and 6 carbon sugars. Here's ribose on the left. This is a 5-carbon sugar. Notice that it adheres to that same basic formula that applied to the 3-carbon sugars. Here it's CH2O in brackets, lowercase subscript n. Now for ribose and for ribulose, n equals 5. So the basic formula is going to be C5H10O5. Okay? Sure enough, that's what the arrow is pointing to up there. When you look at this ribose molecule, what are you seeing? You're seeing a long chain of carbons, 5 long. You're seeing a lot of nonpolar covalent bonds, hydrogen to carbon, carbon to carbon. You're seeing a nice little patch here, this carbonyl, that should be fairly chemically reactive, and you're seeing a lot of basis for water solubility. Okay? Ribulose just has the carbonyl group internal as opposed to external, ketone as opposed to aldehyde. Functionally, practically speaking, not that much of a difference in terms of its behavior with water, in terms of its ability to store energy. We're just talking here about one isomer relative to another. Okay? But look at one of the cool things you can do with these sugars. Here we've got a 6-carbon sugar. So the last slide showed you a 5-carbon sugar, 1, 2, 3, 4, 5. We're ratcheting it up here a little bit. I think this is glucose. We'll find out in just a minute. But you've got 1, 2, 3, 4, 5, 6 carbons, cleverly named by organic chemists. 1, 2, 3, 4, 5, and 6. You have a 6-carbon sugar. You have a you have a carbonyl group at the end. You've got a bunch of hydroxyl groups, lots of high energy bonds going on there. Neat thing about sugars, particularly the 5 and the 6 carbon sugars. In a watery environment like our bodies, like our cells, these 5 and 6 carbon sugars naturally, of their own accord, tend to fold back on themselves such that one end sticks to the other end to make a ring structure. So in our cells, most of the glucose, most of the 6-carbon sugars, isn't this linear molecule, but instead one where one end of the molecule has folded back on the other, and you make this ring structure. Here, the ring structure shows you all the gory details. Everywhere there's an atom, they're telling you what's there. I'll tell you, illustrators must get tired of doing that, because much more common would be this abbreviated ring structure, where at each point where you see an angle, you're supposed to just understand that there's a carbon there, right? Because there's nothing else that's going to be there. If there's something else that happened to be there, they can tell you what it was. If there's nothing else there, you should know there's got to be something there. It's got a valence of 4. Do you suppose it's silicon? No, it's carbon. All right, so you should fill in the blanks there. And you know, they're saying B here is an abbreviated ring structure. You can get even more abbreviated than this. More abbreviated would be to get rid of the H's as well, because you should know that if there's a carbon here, it's got a valence of 4. Here's a bond, here's a bond. There's going to have to be a bond up here. What could it be to? If they're telling you otherwise, it's probably the hydrogen. And they'll still show you where the hydroxyl group is, because the orientation of the hydroxyl group, pointing down or pointing up, could be important. So they'll show you that. But essence of it is this, all right? You can think about these monomers, these carbohydrates, in 2 different ways, as a linear molecule or as a ring molecule, folded back on itself. You know, there are advantages and disadvantages to both. The reality is that most of these 6 carbon sugars in our bodies are folded up as those circles. So we need to be comfortable with the fact that you can dress them up in these different ways. All right. So let me go back and forth here, see if this looks. What I'm doing is I'm looking at this structure. Whoa, get back. I'm looking at this structure. I'm looking to see if they're the same, and I think they are. I see no difference between them. So back here I said, I think that looks like glucose to me. I feel I've been vindicated, because over here they're showing you that abbreviated ring structure that we had just talked through on the previous slide, and it's glucose. All right? So if you wanted to know what the chemical structure of glucose looked like, that's it. The arrow's pointing to it in the upper left-hand corner. Glucose is a 6-carbon sugar. That means CH2O brackets subscript N, where N equals 6. Chemical's formula will be C6H12O6. That's the recipe to make glucose from its base starting atoms. And glucose, remember where I'm going with all this, is polymers. Glucose is a monomer. It's a monosaccharide. Saccharide, sugar, mono, single. So we've got a monosaccharide whose name here is glucose, and we're going to use it as a monomer with other monomers. Why don't we have the other monomer also be glucose? And instead of having 2 monomers of glucose, let's polymerize them together to make a dimer, right, of glucose. How will we do that? We'll do that with a dehydration reaction, because that's how all of these polymerization steps take place. So let's do a dehydration reaction between 2 glucose monomers to make a glucose dimer, and look what you got on the right. On the right, we have exactly that. The water has come out in the dehydration reaction. We've linked together 2 glucoses where we had once had 2 glucose monomers. Now we have 1 dimer with glucose as the monomers, but it's cumbersome to talk about that. Chemists have come up with another name for a glucose dimer. They call that maltose. It's a sugar that you've probably heard of before, but maltose is a disaccharide. Instead of 2 individual glucoses, 2 monomers, 2 monosaccharides, we now have a disaccharide. So there you go. I've told you all about this in abstract forms, but now we're getting into a very practical example of the making of a disaccharide, of a polymer that's 2 monomers long. There's a dehydration reaction. We took the 2 monomers, we linked them together, and we get a dimer. Now, there is this sort of 800-pound gorilla lingering in the room. What is up with that? Right? A glycosidic linkage. Right? Bad news, more jargon. all right? The bond that connects two carbohydrates in a polymer is called a glycosidic bond or a glycosidic linkage. I don't know of any tricks. It's just words, it's vocabulary, but you'll find that in the textbook time and again. I'll probably drop that word several times over the course of the next few weeks. When we're talking about the name of the specific set of covalent bonds that connect two monosaccharides in a polysaccharide polymer, that's called a glycosidic linkage. Okay? Sorry, that's just the way it is. So in A, you see the synthesis of the polymer, the extension of the polymer to make a dimer. The flip side of that is sometimes it is helpful to us to take maltose, that dimer, that disaccharide, and break it up into its component parts, the two individual glucose molecules. You link them together with dehydration reactions, you break them apart with hydrolysis reactions. That's not what the next, well, okay, well, it's close. The next part of this slide B here is a dehydration, but not where you, actually, they're, okay, let me rewind. We'll talk about hydrolysis in just a second. Here's another way that you could link together two monomers. Here we've got glucose and fructose that we're going to link together through a dehydration reaction, making a glycosidic linkage that now gives us a different disaccharide called sucrose. All right? So it doesn't always have to be glucose to glucose. You can do glucose to fructose, and you can make other sugars. I don't know. I thought I had another slide coming. Maybe it'll show up in a minute. If you wanted to break apart maltose into two glucoses, you would do that by attacking this glycosidic linkage with water, driving this arrow in the other direction, essentially, and do a hydrolysis. All right, that's what I was starting to say. Now, what do you do with these chains of sugars? Again, when you're thinking about sugar, the first thing that probably should come to mind is this is a high energy molecule. We're using it to store and or to transport energy. And when you make a really long chain, a really long polymer of sugars, you start to be able to call them things like starch. Starch is just a fancy word that we have, a not so fancy word actually, for a long chain of sugars. That's the polymer that's going on here. It's just a long chain. If the chain has some branches in it, we'll call it amylopectin. If it's just a long straight chain, it's simply called amylose. If it has a whole bunch of branches in it, it's called glycogen. Glycogen tends to be the way that animals store polysaccharides. Amylopectin is the way that plants store polysaccharides. Starches are a way that both plants and animals can store polysaccharides, long strings of sugars. And so it's just showing you here some pictures. These molecules can get so big, these starch granules here can be so big you can actually see them with a microscope. Nucleic acids can become such a long polymer that a single molecule becomes visible even with a light microscope, just because of the size of the molecules. I'm sure some of you are worried about how do you know if you're talking about amylose as opposed to amylopectin as opposed to glycogen. Bottom line is that nobody really worries about that. You shouldn't worry about it either. The concept, though, is that if you've got some branches, if you have something other than 1,4 glycosidic bonds, like you could have a 2,4 glycosidic bond, if you have some non-1,4 glycosidic bonds, now we're really starting to talk about something other than amylose. It's starting to be amylopectin, and there comes a point where there becomes so many that you start to say it's not amylopectin anymore, it's glycogen. And there is no hard and fast rule in terms of when you've crossed the line from one to the other. It's just amylose means no branching, glycogen means lots of branching, intermediate amylopectin. All right, so the primary utility of polysaccharides for living things is energy storage. And a starch that has a whole bunch of those 1,4 glycosidic linkages, a long chain of glucoses that way, is exactly what we use starch for. Energy storage, energy transportation. Big chunk of change in terms of energy that you can move from one part of an organism to another part, or you could store and save for a rainy day, perhaps literally. But leave it to nature to find quirky sort of alternative uses. They've got this machinery in place to string together chains of saccharides, to make polysaccharides. It shouldn't surprise you guys. It might surprise you now. It won't surprise you by the end of the class that you got that infrastructure in place for making starches for the purpose of energy storage. Maybe there's a way to put a little twist on it to use that same sort of basic strategy, that same machinery, but have it have a different function. That's what's going on with cellulose, right? You're using essentially the same enzymes, the same chemical strategies, but here, whereas starch is used for energy storage, cellulose sure has a lot of energy associated with it, but because of this little subtle difference, alpha glucose as opposed to beta glucose, that subtle difference ends up causing the molecule to have a very different set of properties and a very different set of uses. Living things use polysaccharides not just for energy storage and transport, but in certain circumstances, with certain twists on the system, they can use it for structural purposes. So trees, plants, they'll make cellulose to help support their infrastructure. It's literally used for structural purposes. The difference between starch and cellulose, again, is very subtle. Alpha glucose for starch, beta glucose for cellulose, and also another variant on that is chitin. Chitin, the exoskeleton of arthropods, and leave it at that, the exoskeleton of arthropods, insects, that exoskeleton is just another twist on glucose polymers. All right? So for you and I, for our bodies, we use starch, we use polysaccharides for energy storage and energy transportation. Plants and some insects also adopted the same sorts of machinery to give polysaccharides another function, and that is it's playing a structural role. Plants to make wood, arthropods to make exoskeletons. All right. Well, believe it or not, that's what I wanted to tell you guys about carbohydrates. I saved the snoozy part for the last 6 minutes of the lecture. All right, so this is your chance to get a 6-minute nap, because I'm going to talk with you about lipids. I'll tell you, lipids are boring, all right, for lack of a better word, and they're only loosely fitting into this category of polymer. But here's the deal with lipids. Again, lipids are essentially fats, and they are called polymers because we tend to find them in trimers, where there is a glycerol molecule that holds together 3 fatty acids. Here you can see one getting added on as part of a dehydration reaction. If you wanted to pull it off after it's there, you have to do a hydrolysis. So hence, a polymer. But these tend to be short polymers, only 3 that will be associated with this glycerol. So here we're adding on a fatty acid. Here, palmitic acid. Check it out. What do you see there? Lots of carbon-carbon, lots of carbon-hydrogen bonds. No basis at all for solubility with water. Very high energy bonds. If carbohydrates were good for energy storage and transportation, fats are really good for energy storage. Right? They take it to another level. Here, every bond is a high energy bond. And that's exactly why there's so many more calories associated with an ounce of butter than there is with an ounce of sugar. There's an enormous amount of difference in terms of the calories associated with an ounce of butter in an ounce of sugar. And again, it's ultimately due to this structure. So If you add on 3 of these fatty acids to a glycerol, you end up with a fat molecule. You could call that a triacyl because of the fats, triacyl glycerol. They don't always have to be the same fatty acid that gets added on, but this is the way that we tend to store our fat molecules. I'm sure you've all heard about saturated as opposed to unsaturated fats. It boils down to this. For a saturated fat, every carbon is associated with 2 in the chain. Every carbon is associated with 2 hydrogens. It's saturated with hydrogens. On the labels for food and such, they dropped off that saturated, they dropped off the with hydrogens part. It's just saturated, but it's saturated with hydrogens. An unsaturated fat is one where there are some places where the carbons don't have 2 hydrogens. Instead, there are double bonds between 2 carbons to fill out the valence requirements for the carbon. Okay, so a saturated fat is one where you've got just nothing but carbon and hydrogen. An unsaturated fat has some spots where you've got carbon that are engaged in these double bonds. Funny thing, saturated fats at room temperature tend to be solid. Ultimately, it's because they pack well against each other into a fairly regular matrix. They can hang out together in a nice compact space. That makes them solid. Unsaturated fats, because of those double bonds, have kinks, literally kinks in that carbon chain, and they can't really pack into each other that well because they got this thing poking out at a weird angle. So unsaturated fats tend to be liquid at room temperature. Saturated fats tend to be solid at room temperature. Olive oil, right? Butter. A close-up picture of butter. A close-up picture of olive oil. One last phospholipid, or one last lipid polymer to talk about here today, and we're done. Here, we've got, instead of glycerol with its 3 carbons, here we've got glycerol with its 3 carbons where one of them is attached to a phosphate group. So it's the same glycerol. Before, we were talking about dangling 3 fatty acids off of them. Here, we're talking about dangling 2 fatty acids off of the glycerol and a phosphate group. Specifically, a phosphate group that has a choline attached to it. Fancy name, this is phosphatidylcholine. The space-filling model of this structure looks like this. This is also sometimes referred to simply as a phospholipid. What do you see when you look at this molecule? I'll tell you what I see just to make this go quickly. Lots of hydrophobicity over here. Water wants nothing to do with this. Lots of hydrophilicity up there because of negatively charged phosphate. In a word, this is a schizophrenic molecule. Quite literally, it has a dual nature. Part of the molecule wants nothing but to be wrapped up and rubbing up against water molecules, and part of it wants nothing to do with water molecules. So there's a part of this molecule that's hydrophobic, a part that's hydrophilic. How do you suppose a bunch of those molecules would like to hang out? They would like to hang out as a phospholipid bilayer. They have the phosphate groups on the edges where they can interact with water, and the fatty acids in the middle where water is excluded. That is what cell membranes are made out of. So that's a primary application. Another sort of ancillary application of lipids is we can use those for the structural purpose of making membranes in addition to the primary purpose of storing energy. Lots and lots of energy. All right, so let's call it a day. Come back here on Thursday and we'll have fun talking about proteins and nucleic acids.